Hey everyone, and welcome. So have you ever really stopped to think about how an application buried deep inside a Kubernetes cluster manages to talk to the rest of the world? It can feel like a bit of a black box, right? Well, today we're going to pry that box open and map out exactly how it works. Let's get into it. Okay, so you've done all the hard work. Your application is containerized, it's running beautifully inside a pod in your cluster. That's awesome. But now what? How does a user sitting at their computer halfway across the globe actually connect to it? That is the fundamental question we are going to answer right now. So here's our game plan. We're going to start from the very core, looking at how services talk to each other inside the cluster. Then we'll start opening things up to the outside world, from the simple methods to the more advanced. We'll even take a look at the future with the Gateway API. And most importantly, we'll wrap up by talking about how to keep it all secure.
All right, first things first. Before we can even think about getting traffic from the outside world, we have to understand how traffic moves around on the inside. This is the bedrock that everything else is built on.
Here is the absolute core challenge of Kubernetes networking. Pods, well, they're designed to be disposable. They're what we call ephemeral. They can be created, destroyed, or moved to another machine at any moment. And every single time that happens, poof, it gets a brand new IP address. So how in the world are you supposed to have a stable connection to something whose address is constantly changing?
And the magic answer is the Kubernetes service. You can think of a service as a stable, logical front door for a group of your pods. The service gets its own permanent IP address and a consistent DNS name that doesn't change. Behind the scenes, it's doing the hard work of keeping an up-to-date list of the healthy, running pods and just forwards traffic to them. It's the abstraction that makes this whole dynamic environment actually work.
Now, the most basic and the default type of service you can create is called a cluster IP. And the name gives it away, right? It gives your service an IP address that only works from inside the cluster. This is your bread and butter for internal communication, like having your front-end pods talk to your back-end API pods.
I really like this analogy. It makes it super clear. A cluster IP is just like an internal office phone extension. You know, anyone else in the building can dial extension 451 to reach the accounting department. But if a client from outside tries to dial 451 on their phone, nothing happens. It's a private number, meant only for internal use. Okay, so our internal phone system is working great. But what if we actually want to receive calls from the outside world? It's time to connect our cluster to the internet. Let's see the simplest ways to do that. You can think of these exposure methods as climbing a ladder. We start on the ground with cluster IP, which is totally internal. The first step up is node port, which gives us some very basic external access. And at the top of the ladder for single service exposure, you have the load balancer type, which is tightly integrated with cloud providers.
So what exactly is a node port? Well, it's pretty literal. When you create a node port service, Kubernetes opens up a specific high-numbered port on every single node in your cluster. That means you can now access your service by hitting the public IP of any of your nodes on that specific port. It's fine for testing or a quick demo, but you can probably already see the downsides, right? You have to know the IP of at least one node, and what happens if that node goes down?
Now we're talking. If you're running your Kubernetes cluster in a cloud like AWS, GCP, or Azure, this is the real deal. When you create a service of type load balancer, Kubernetes automatically calls out to the cloud provider's API and provisions a native external load balancer for you. This gives you one single, stable, public IP address that you can point your DNS records at. This is really the standard production-grade way to expose a single application. Let's bring back our phone analogy. A node port is like knowing the direct number for the company's switchboard operator. Yeah, they can connect you, but it's a bit clunky and indirect. A load balancer, on the other hand, is the official, public 1-800 number for the entire company. It's reliable, professional, and the way customers are meant to get in touch.
But hang on a minute. A whole cloud load balancer for every single service? That's going to get really expensive, and it sounds like a nightmare to manage. There has to be a smarter way, a single front door for all our services. And that brings us to Ingress.
No, seriously, just think about a real microservices application. You might have 20, 30, maybe 100 services. Are you actually going to spin up and pay for 100 different cloud load balancers? Your finance department would have a heart attack, and you'd be stuck managing a giant list of IP addresses. There just has to be a better way.
And of course there is. It's called Ingress. The core idea behind Ingress is simple but powerful. You only use one external load balancer.
That load balancer sends all the traffic to a smart reverse proxy running inside your cluster. This proxy, the Ingress, looks at the incoming HTTP requests and acts like a traffic cop, routing them to the correct backend service based on a set of rules you define.
And this is what makes it so smart. It's not just blindly forwarding traffic. It can look at the host name. So requests for api.example.com go to your API service, while requests for blog.example.com go to your blog service. Or it can look at the URL path. So example.com/videos goes to one service and example.com/images goes to another. It's incredibly flexible. But, and this is a critical point, the Ingress resource itself is just a set of rules. You need a piece of software called an Ingress controller to actually implement them.
Now, Ingress has been the workhorse of Kubernetes networking for years, and it's fantastic. But as people built bigger and more complex systems, they started to hit its limits. So the community got together and designed its successor, the more powerful and flexible Gateway API.
You see, one of the main challenges with Ingress is that it's a bit of a monolithic resource. The entire configuration for all your routing is in one place. That gets really messy in large organizations, where a central platform team might manage the infrastructure, but different developer teams just want to control the routing for their specific application. The Gateway API was designed from the ground up to fix this.
This table really highlights the key differences. And I want you to focus on that top row, role separation. This is the absolute game changer. With the Gateway API, your infrastructure team can create a gateway resource, which represents the load balancer. Then, application teams can independently create and manage their own HTTP route resources to route traffic to their services and attach them to that gateway. It cleanly separates concerns. On top of that, as you can see, it's just more expressive and extensible, with built-in support for more protocols and a proper standardized way to add features.
Okay, we have spent all this time learning how to poke holes in our cluster to let traffic in. Now it's time for arguably the most important section. How do we do it all safely? As soon as you open the front door, you'd better put a guard on duty. And let me be perfectly clear on this. Every single time you expose a service, you create a potential attack vector. Every open port is a new way for someone to try and get in. Managing this risk isn't an afterthought. It's a core responsibility of running any application.
Here's a fact that might surprise you. By default, in a standard Kubernetes cluster, any pod can talk to any other pod. The network is completely flat and open. That's where your primary weapon, the network policy, comes in. Network policies are basically a firewall for your pods. They let you write explicit rules to lock down communications, like saying only pods with the front-end label are allowed to talk to pods with the database label on port 5432. This is absolutely essential.
But of course, one tool is never enough. Real security is about defense in depth, having multiple layers of protection. So this checklist is crucial. You have to use network policies for internal traffic. You must enforce TLS to encrypt all external traffic. You need to use role-based access control, or RBAC, to limit who even has permission to create these powerful networking objects. You should be hardening your pods with security contexts, and you have to be constantly scanning your container images for known vulnerabilities. Each one is another layer in your defense.
So we've covered the entire journey, from a totally isolated pod to a globally available, securely routed application. The tools Kubernetes gives you are incredibly powerful, but that power brings us to our final and most important question, the one I want you to take back with you and think about. Now that you know all the different ways to open the door to your cluster, have you put all the necessary locks on it?